So we can start talking about radiation, and to do this, we need to get some definitions clear. First, we have a definition for radioactivity. That's just the spontaneous decay, so it happens kind of without warning, that turns mass from an atom into an emitting ray of energy. So we're going to convert mass into energy. And the equation that governs this, we already know this, is going to be the E equals mc squared. Energy and mass can be converted between each other. And in particular, there's something called nuclear radiation, which is just a specific property of radiation where it can be ionizing. So that means that it can emit energy that's able to strip electrons outside of an atom, which is basically what an ion is, an atom with stripped electrons. So to understand radioactivity, we first need to understand this conversion of mass into energy. And to do that, we need to know a little bit more about atoms, and in particular, the nucleus. So to understand the nucleus, we need to kind of get some terminologies in place. First, we have the word nucleon. Nucleon is a way that we can describe the particles that are inside of the nucleus. So that would just be your protons and neutrons. Protons and neutrons are nucleons. When we're discussing mass of the atom, in particular the nucleus, we use a unit that's called the AMU. And the AMU is short for atomic mass unit. There are some conversion factors we have for AMUs. In the unit AMU, we typically write as 1 with a little u next to it. So that's the little u represents the AMU. And that's equal to 1.66 times 10 to the negative 27 kilograms. Or we can do this in terms of energy, since radioactivity is interested in converting between mass and energy. It's going to be 931.46 mega electron volts, again, which is a unit of energy, divided by Coulomb squared. As we continue to talk about the nucleus, we need to talk about nuclides. Nuclides, specific combos of protons and electrons. Protons and neutrons. And we have some shorthand letters that we use to represent different quantities in describing nuclides. We have A. A is called the mass number. And it's equal to capital N plus capital Z, where capital N is the number of neutrons in a nuclide, and capital Z is what we call the atomic number, which is the number of protons. So we can think of the mass number is equal to number of neutrons plus the number of protons. We have another thing, another symbol that we use, X, the symbol X. That's typically used to represent the general symbol for an element. So if I'm just describing something in general, I'd use the letter X. If I'm talking about a specific element, that symbol would be the symbol for that element. So for example, hydrogen would be H, helium would be He, so on and so forth, whatever you see in the periodic table. Now we can take these nuclides and we can do some fancy things with them. Now most of the time, the number of protons inside of my atom is going to be equal to the number of electrons. So the atomic number gives you the number of protons, and it gives you the number of electrons. If I start changing this, if I have an atom that has an unusual number of electrons, we call that an ion. And then the last little bit to know about the substructure of the nucleus is that if I have nuclides, with the same Z, so the same atomic number, but different N, so different number of neutrons, I've created something called an isotope. This is kind of some terminology that helps us to keep things straight when discussing the substructure of the nucleus. And two more important points to make before we move on and discuss some radioactivity more specifically. First, we want to know, when inside the nucleus, we've got these protons and we've got these neutrons. And something that seems strange is positive charges hate other positive charges. Positive charges repel. So we want to have an idea of why the nucleus doesn't fly apart, because it's all these positive charges really close to each other. Now, the reason the protons are held together is something called the strong force. The strong force is responsible for holding the nucleus protons together. The last thing to know before we go into radioactivity and discussing types of decays, we want to know how big the atom is. And it turns out that the atom size, the physical size of your atom, is proportional to the mass number. And this just makes sense. The atom should be bigger if it has more nucleons inside of it. And we can quantify this by R is equal to R naught times A to the 1/3. And this allowed us to calculate a radius of any atom where R naught is equal to 1.2 femtometers. And this is a very, very tiny unit of length. It's 1.2 times 10 to the negative 15 meters, which makes sense because atoms aren't that big. So now that we have some nucleon terminology in place and we know these letters and what these letters represent, we can turn to learning about some nuclear radioactivity mechanisms. So there are three types of radioactive decay, and we're going to start with alpha decay. So alpha decay involves something called an alpha particle. But an alpha particle is just another name for a helium nucleus. So a helium nucleus is involved in alpha decay. And we can write this in symbol form as some element X, remember that represents a symbol, with a little subscript N, represents the number of neutrons, Z is the number of protons, and A is the mass number. And if this is going to undergo an alpha decay, it's going to turn into a new element. Some new element Y. It's going to have N minus 2, so we're going to lose two neutrons. Z minus 2, we're going to lose 2 protons. And A minus 4, because we're going to lose 4 total nucleons. Plus 4 nucleons total, 2 protons, 2 neutrons, which is the element helium. So we've taken this particle, this element, whatever it is, this element X, and we've lost a helium nucleus. So we can see right away that every single one of the symbols that we have, we've kind of lost the equivalent amount that's contained inside of the helium nucleus. So we have N. I have 2 neutrons in helium, so I have to do N minus 2 in my radioactive decay, because I need to conserve the numbers of charges on each side. I have Z, the number of protons. Helium has 2, so I need to take 2 away from my radioactive decay process. And then I've total have a amount of 4 nucleons that I've eaten up inside of this helium, so I need to take those away from the reactive product, the radioactive decay object. Okay. So this is our radioactive decay for alpha decay. We also have a decay type called beta decay. Greek letter beta. And there's a few different types of beta decay. There's a negative beta decay where we lose a negative beta particle. So I start with my element X, a little n, represent the neutrons, Z representing the protons, A representing the mass number. And what I'm going to get out of this is Y, some element that's going to lose a neutron, is going to gain a proton, and have the same mass number. Because I need to conserve my charge, this beta particle is actually a negative particle, negative electron. And then I lose something, this little Greek letter nu sub e with a line over it. This is called an anti-electron neutrino. And this is just one type of beta decay. I can also have beta plus decay, where I get a positive beta particle. So I start with my same situation, my element X with n neutrons, Z protons, and A mass number. I keep the same mass number. I get my resultant element Y, which is going to have now one extra neutron, and I'm going to lose a proton, plus the beta plus particle, which is a beta plus, which is an anti-electron called a positron, and then plus a regular electron neutrino. And all these little decay chains, these equations, are conserving the total number of charges on the left and right side. You should have done this in a chemistry course, and we're repeating it in physics. Final type of beta decay, we have electron capture. Let's start with our same symbol X with n neutrons, Z protons, and A mass number, and we're going to add an electron to this. So by doing that, that changes the right-hand side. We're adding an electron, so we're losing one charge. So to keep the charge balanced, I need to subtract off a proton. I need to make this more negative by subtracting off that proton. And we have Y, n plus 1. I need to add a neutron so that I maintain my mass number, plus my electron neutrino ends up on the other side. Those are all the reactions that we can have for beta decay. Last but not least, we have something called gamma decay. So this is how you get characters like the Incredible Hulk. So in gamma decay, we take X with some number of neutrons, and we're going to create X with N plus some gamma ray particles, some energies. Okay. And anytime we're doing these reaction chains, we have to keep in mind some conservation laws. And I will go to the book to read more about these, but the conservation laws tell us that we need to conserve electron family number and conserve the number of nucleons. So the total number of particles inside of your nucleus. And one of the last primary uses of radioactivity is in studying something called half-life. So half-life, we typically represent with the letter T, with a little 1/2 subscript next to it. And this is the time in which there is a 50% chance that a nucleus will spontaneously decays. And we can write this equation out. We can write this in equation form and figure it out. N, the number of nuclei that you have, is equal to N naught, the number of nuclei at some starting time, times e to the negative lambda t, where N0 is equal to the number of nuclei you start with. Lambda is something called the decay constant, which you can write in terms of the half-life of lambda equals 0.693 over t to the 1/2. So that's what we can plug in for that lambda. And then t is the time that you're interested in knowing how many nuclei you have left. We use this all the time in a process called radioactive dating to figure out how old things are. Works for rocks, works for fossils, works for meteorites. It's very useful in a variety of applications. And radioactive dating uses R equals delta N, the number of nuclei, over delta T, where the units of R are known as the becquerels. And 1 becquerel is equal to 1 decay per second. So this tells you how fast something converts into losing its nuclei. And that decay rate you can calculate using this radioactive dating equation.